Before we try to define 2 raised to the power of irrational numbers like pi, let's just review the logic for how we reasoned about what things like 2 to the power 0 or 2 to negative powers or 2 to rational powers should be, because there was a definitional choice there. So to see that, let's start by thinking about this function f of x is 2 raised to the power x, and to begin we're going to assume that these two inputs a and b are positive integers, because then the question just reduces to counting factors of 2. So we'll ask, what are f of a plus b and f of a times b in terms of f of a and f of b? So to start, f of a plus b, well, since a and b are positive integers, this is 2 to the power a plus b, which really just means we're multiplying 2 times 2 times 2 times itself for a total of a plus b times. But since multiplication is commutative and associative, we can just split this up into 2 groups, where the first group has a of those copies of the factor 2, and the second group has b of those factors, so one of these is a times, and and the second is b times. And of course that's simply f of a, because this is 2 to the power a, times f of b. So this is a very nice property. It works for integers based on counting. F of a plus b is f of a times f of b. So now let's think about the second question. What is f of a times b? Well, this is going to be 2 to the power a b, which is 2 times itself for a total of ab times. But we can split that total of ab times into b copies of 2 multiplied by itself a times. So here's one group of 2 multiplied by itself a times, and then we're going to multiply by another copy of 2 multiplied by itself a times, and we're going to repeat those groups of a so that there are b total groups of a. So each of these groups has a factors, and there are b of the groups, so a times. And then there are b of these big groups, b times. Okay, but then each of these groups is 2 to the power a, and there are b of them. So this whole thing is 2 to the power a raised to the power b. So this is the usual power to a power rule, but now we can see explicitly why it works when these are integers, because we're just grouping factors. So when we move on, since this reasoning that we've used here only applies to integers, we haven't defined what we mean by a number raised to a 0 power or to a negative power. So there's a choice there. You can define that to be whatever you like. Some definitions are better than others. But we're going to try to pick a definition which maintains these properties, that f of a plus b is f of a times f of b, and f of a times b is, oops, I should have written this as f of a, since 2 to the power a is f of a times b. So f of a times b is f of a raised to the power b. Okay, so let's ask the question, now how should we define f of 0, which is 2 raised to the 0 power? And again, there's a choice here, but let's choose the definition of f of 0 to maintain this property. We saw in the previous slide that for positive integers, f of a plus b is f of a times f of b. 0 is no longer a positive integer, but if we want to extend our definition so that this identity is still true, we can figure out what f of 0 has to be, right? Because for this to be true, if I set a equal to 0 and b equal to 0, this equation tells me f of 0 plus 0 equals f of 0 times f of 0. So, of course, this thing on the left, since 0 plus 0 is 0, this whole thing simply means that f of 0 equals itself squared, f of 0 squared. So there's two possibilities. Either f of 0 is 0 itself, because then this equation would be true, because 0 equals 0 squared, or if f of 0 is not equal to 0, then we can divide both sides by f of 0. So when I divide by f of 0 on the left, that gives me 1. When I divide on the right, that gives me f of 0. And that means we can conclude f of 0 equals 1. So as you probably know, this is the definition we're going to choose to keep, that 2 to the power 0 equals 1. But now you see that this was a choice, and you know the reason why we made that choice, because that choice keeps this true, this multiplicative property, that if you add two things inside, they multiply outside. Okay, so that's the punchline. We picked number raised to the 0 power equals 1 to make this identity still true. Next question. How should we define negative powers, so 2 raised to a negative power? And again, this is a choice. Nothing forces us to define it this way. But we're going to continue to be guided by this property. If we want f of a plus b equals f of a f of b, that tells us what f of a negative integer should be, right? This is f of minus n, where n is positive, so the thing inside is negative. How do we figure out what that should be? Well, here's f of a plus b, where I've set a equal to n and b equal to minus n. But of course, n plus minus n equals 0, and from the previous slide we saw that f of 0 is 1. So let's just continue this equation. This should be f of n plus negative n. We want to be f of n times f of minus n. That's just using the property we'd like to be true. That has to equal 1, because that sum gives 0. But f of n is 2 to the power n, because we've assumed n is a positive integer. 2 to the power n times f of minus n equals 1, and then we can conclude f of minus n equals 1 over 2 to the power n is simply f of n. Good. So again, this is the conclusion we are forced to accept if we want to keep this property true. So here, this is a derivation of sorts of the rule that a negative exponent is the reciprocal of the same number with a positive exponent. And again, this was a choice all motivated by this equation. Okay, last question. How should we define f of rational numbers? So this is the question of how we define 2 to the power p over q for some integers p and q. And again, this time we're going to choose the definition in order to make this equation, which was true for integers, still true for rationals. So what do we have to do to make f of a times b equal to f of a raised to the power b? Well, to get that, we have to take this f of p over q, which of course is equal to p times 1 over q, right? That's the product of these two things. So I'm setting a equal to p and b equal to 1 over q. That has to be equal to f of a, which is 2 to the power p, raised to the power b, which is 1 over q. Or I could flip a and b. Since multiplication is commutative, I could have done it in the opposite order, 2 to the power 1 over q raised to the p. Either of those is fine, and this is a rigorous definition assuming we know how to take qth roots, because some number raised to the power 1 over q is the qth root of that number. So thus we've defined 2 to the power x for any positive, negative, 0 integers or rationals. So we've defined 2 to the x for x in q, and again, I just want to stress, mostly by assuming this thing about f of a plus b equals f of a times f of b. That did most of the work. We wanted this to be true, and that gave us a guideline to choosing definitions of 2 to the power 0 and 2 to the negative powers. It's another bullshit detector question. If you ask someone why 2 to the power 0 is 1, they will usually just tell you, oh, it's a definition. Any number raised to the 0 power is 1. But why did you choose that definition? This is the answer. We picked the definition so this thing, which we only knew at the beginning was true for positive integers, we chose the definition so it would still be true for 2 to the 0 or 2 to the negative powers. Okay, that ends the review of exponentials of rationals. Next, we'll move on to asking about reals.